So here we have a statics problem where the angles are not the same. Again, there's two strings attached on the ceiling. They come together. From that, there's a mass suspended. The mass has a mass of 2 kilograms. But notice that this angle between the ceiling and the string is 30 degrees, and this angle between this string and the ceiling is 45 degrees. What are the tensions in those strings? What we do know is that the sum of all the forces acting in the x direction must add up to 0, and the sum of all the forces in the y direction must add up to 0, because this is a static situation. Nothing is moving, nothing is accelerating, which means the sum of all the forces in any direction must add up to 0. So we now have to identify the sum of all the forces in both the x and the y directions. So here we can see that we have, let's call it tension 3 acting downward, which is equal to the weight of this object. We have tension 1 pulling this way, and we have tension 2 pulling this way. So now what we're going to do is subdivide tension 1 and tension 2 into their x and y components. So you can see that this here would be tension 1 in the y direction, and this component here would be tension 1 in the x direction. Notice that if this angle is theta equal to 30 degrees, then this angle must be theta equal to 30 degrees as well, because alternate interior angles are equal, which means that this becomes the opposite to the angle, and this becomes adjacent to the angle, which means this is T1 times the cosine of theta, and this is T1 times the sine of theta. And of course, I should write theta 1 because theta 1 is the one that is 30 degrees. We can do the same for T2. Let me grab a different color. So here we have T2x, which is equal to T2 times the cosine of theta sub 2. Here the angle is 45 degrees. Alternate interior angles, of course, are equal. And there is T2y, which is equal to T2 times the sine of theta 2, which of course is sine of 45 degrees. So now we can go ahead, and now that we have all the components, we can plug that into our equation here. So in the x direction, there's only two components. I have T1 in the x direction, that's in the negative direction. I have T2 in the positive direction, so I can write this as T2 times the cosine of theta 2 minus T1 times the cosine of theta 1. So that's our first equation, which have both T1 and T2 in them. Two unknowns, one equation. Not good enough to solve, so we need a second equation. All the components in the y direction. We have two positive components. We have T1 times the sine of theta 1 plus T2 times the sine of theta 2 minus mg, T3, which is of course mg, the weight of the mass there hanging from that string. And now we have two equations and two unknowns. So the process is exactly the same as in the previous example, but now we realize that T1 and T2 will not be the same because theta 1 and theta 2 are not the same. All right, so let's go ahead and take our first equation and solve it for T2 or T1 in terms of the other one. All right, so we can go ahead and set these equal to each other. Moving this over to the other side, I can write that T1 times the cosine of theta 1 is equal to T2 times the cosine of theta 2. I can go ahead and divide both sides by the cosine of theta 1. And so T1 is equal to T2 times the cosine of theta 2 divided by the cosine of theta 1. So this is equal to T2 times cosine of theta 2. Theta 2 is 45 degrees, so that's a cosine of 45 degrees divided by the cosine of 30 degrees. All right, 45, take the cosine of that, divided by 30, take the cosine of that, equals, and it's 0.8165. So T1 is equal to 0.8165 times T2. I kept a few extra significant figures so I don't have a round-off error. Now I can go ahead and plug that into my second equation, getting rid of one of the two unknowns and solving the other unknown. So now I have, let's see here, 0 is equal to, instead of T1, I'm going to write what T1 is equal to in terms of T2. 0.8165 T2 times the sine of theta 1 plus T2 times the sine of theta 2 minus mg. All right, I now have an equation with just the one unknown. Let's plug in everything that we know. So we have the sine of theta 1. Theta 1 is 30 degrees. The sine of 30 degrees is 1/2. So we have 0 is equal to 8. Oops, I'm getting a little ahead of myself here. So we have 0.8165 T2 times the sine of 30 degrees plus T2 times the sine of theta 2, which is 45 degrees, the sine of 45 degrees, minus mg. Of course, m is 2 kilograms, and g is 9.8 meters per second square. Okay, so sine of 30 is 1/2, so 1/2 times this. So divided by 2 equals, so we have 0 is equal to 0.408 T2 plus 45, take the cosine of that, which is 0.707 T2 minus 19.6, and of course kilograms meters per second squared, that's units of newtons, so we get 19.6 newtons. There we go. All right. So now we can, of course, combine those two. So we have 0 is equal to 4.08 added to this, that would be 1.115 T2 minus 19.6 newtons. So now when we solve this for T2, we have 1.115 T2 equals 19.6 newtons by moving this to the other side and moving the equation around. And then, of course, dividing both sides by 1.115. Let's make sure I did that correctly. 11, yep, that looks correct. So finally, I can say that T2 is equal to 19.6 newtons divided by 1.115. So 19.6 divided by 1.115 equals, and so T2 is equal to 17.6 newtons. All right, now that we know what T2 is, we then go back over here and we say that T1 is equal to 0.8165 T2, 0.8165 times 17.6 newtons, 0.8165 equals, and so this is 14.4 newtons for T1. And there you go. So it's a little bit more complicated because T1 and T2 are not equal to each other, but you can find the relationship. Then you plug that in here, and then you do the same as before, and you find your two tensions. Notice that tension 1 is smaller than tension 2. It looks like tension 2 carries more the weight of the object than tension 1, and therefore tension 1 is smaller. And so that is how you do that problem.